Hey everyone, welcome to Talks at Google. I'm Matt Bonjovi, and I'm delighted to be welcoming our two special guests for today, Peter Coveney and Roger Highfield. Roger is the Science Director of the Science Museum Group in the UK, Fellow of the Academy of Medical Sciences, a visiting professor of public engagement at Oxford, and a widely read author among a long list of other accomplishments. Peter is a professor in physical chemistry at University College London, Director of the Center for Computational Science, and Associate Director in the Center of Advanced Research Computing, and also a widely read author, again, amongst many other accomplishments. Peter and Roger have previously co-authored several books together, and they are here with us today to discuss their latest work, Virtual You: How Building Your Digital Twin Will Revolutionize Medicine and Change Your Life, which is a panoramic account of efforts by scientists around the world to build digital twins of human beings. These virtual copies of ourselves will usher in a new era of personalized medicine, one in which your digital twin can help predict your risk of disease, participate in drug trials in your stead, shed light on the diet and lifestyle changes that are best for you, and help identify therapies to enhance your well-being. Today, we'll be talking through some of the topics covered in Virtual You, and throughout the discussion, you might have some great questions that you'd like answered. If you do, please go ahead and add those to the chat on the right. We will have time shortly for Roger and Peter to answer some of your questions, so be sure to get them in early. But first, Peter, Roger, thank you both so much for being here.
It's great to be here, Matt. Lovely to be with you all.
Thank you.
Very
and
nice
to start us off, we'll watch a short video that you guys put together that kind of outlines the promise of what we're talking about when you say Virtual You. So let's go ahead and take it away with Virtual Humans.
Our bodies are exquisitely complex machines. In our efforts to care and improve them, we look to those who push the limits of what is humanly possible, such as athletes. Now, you would say, what can we learn from them if every athlete is different? If they achieve peak performance through customized diets, training, and technology. As it turns out, we too are all different. That is to say, there is no single lifestyle, no diet, no medication that will work equally well for all of us. If this is so, how can we get the best out of our bodies? Now, imagine a virtual human, not made of flesh and bone, one made of bits and bytes. And not just any human, but a virtual version of you, accurate at every scale, from the way your heart beats down to the letters of your DNA code. You know that many drugs only work well on some people and can cause serious side effects in others. The reason is variations in DNA, our genetic differences. But we understand how these DNA differences change the building blocks of your body, the proteins, and we can simulate in a computer how drugs interact with them. By testing drugs on your virtual body, your doctor may eventually be able to test a wide range of drugs and select precisely the right one to suit you. But sometimes, choosing the right drug is not enough. We must also be able to deliver it to a precise target in the body. Take inhaled drugs, for instance, which can end up in the walls of your nose or at the bottom of your lungs, depending on the intricacies of your particular respiratory system. Using supercomputer simulations based on scans of your lungs, we can predict with high precision where particles will flow, and then design devices that can deposit drugs exactly where your body needs them. Well, obviously, mastering drug delivery means controlling the body's main transport network, your circulatory system. By simulating the movement of red blood cells and other cells, we can understand important protective processes, like those that prevent blood loss after an injury. Virtual humans could help doctors to plan risky surgery too. They could be used to work out how to reach an aneurysm deep in the brain that is at risk of rupture, which could cause a stroke. Surgeons could then try out the best treatment or implant to suit the location and shape of that particular aneurysm. They could even double check that the implant will not cause problems, such as clotting, before they try it out on you. Physics, chemistry, and biology intertwine in your circulatory system to drive the most remarkable pump that evolution has ever created, the heart. To create a virtual heart, processes have to be modelled at multiple scales, from the contraction of muscle to the blood flowing through its chambers to the movement of charged atoms during a contraction. Virtual hearts already beat within supercomputers, where we can test the effect of different drugs or pacemakers, but also more fundamentally, to understand the way an individual's heart works. Your virtual avatar will not only be built in your image, it will also move like you. We can use it to calculate the forces and the mechanical stresses that are constantly induced on your bones, and predict the risk you will suffer a fracture. Doctors can also use virtual humans to work out how diet, exercise, or drugs can help those with brittle bones. And what if we go even further than treating disease, using virtual humans to prevent illness? Within a supercomputer, many virtual versions of you can explore small changes in your lifestyle and how they affect your health, aging, and quality of life. Virtual humans, helping you to figure out the very best that you can be.
Awesome. That was amazing. And if I can kind of briefly sum up what we just saw, the clip is indicating that we're working towards this world where we have really detailed models that are able to predict and match all of the physical and biological processes that are going on in our bodies. And that if we have these, then we can really entirely shift how we think about our relationship to medicine and our personal relationship with medicine.
That's exactly right. I mean, you can think of medicine a bit like, current medicine's a bit like trying to drive down the road, looking in a rear view mirror the whole time. You're always referring back to trials done in the past on people who are a bit like you in circumstances that might be a bit like your circumstances. And really what Peter and I are arguing for in Virtual You is the use of more modeling, where you can actually make medicine truly predictive and personalized for the first time. So in effect, for the first time, you're looking out of the windscreen rather than in the rear view mirror the whole time.
Yeah. Yeah. And I think one of the things that we just saw in that video as well is lots of snapshots of particular, almost like implementations that you can have. You can have a model of different levels of the heart. You can have a model of different things. How much of that is stuff that's ongoing today and like being used today versus things that you're looking at maybe like in the near future?
Well, all of the things that you saw in that video are real-world simulations that have been done and run on supercomputers. Typically, the credits indicated where they were carried out. And typically in that project, which is European-funded, most of them on many European supercomputers. So they're illustrative of what you might call digital twins of different components of the human body, which has the massive challenge of being incredibly multi-scale. from the genome level up to the whole human and indeed beyond. Because if we're dealing now, as we are, with things like pandemics, clearly we need to look at infectious disease across populations of humans. And we're also working on in silico clinical trials, which can be components of the human body run as multiple different instances all on a particular machine. So you get a population which simulates individuals, and therefore you can do an in silico clinical trial that way rather than, say, using animal testing or actual human beings. The extent of that is already quite substantial. And obviously, as time goes by, one expects to integrate more and more of these bits and pieces together.
Yeah. I mean, just to jump in there, Matt, you know, I must say when we started writing the book a few years ago, I knew that we had very sophisticated virtual hearts where you can actually make a digital twin of a person's heart now. Peter's done amazing work on recapitulating the whole 3D circulatory system of a South Korean woman, for example. I knew there were various other bits and pieces, but actually what blew me away in helping Peter with the book is how sophisticated, for example, simple virtual cell models are. And even the brain, which has huge challenges for very obvious reasons. You know, there's a clinical trial underway in France where they've mapped out the kind of connectome of patients for epilepsy surgery. And it's surprising just how much digital twin research is already being used out there in clinics.
Yeah. Yeah. And one of the things that you were mentioning there is that there's different almost granularities at which you can do these simulations. You can do these cell level, atomic level, or you can do sort of larger heart system circulation. How do we go about thinking about which of those are needed and what like the collection that's needed to make actionable decisions might be? Because I could imagine bigger scale things, you might capture some of the information of smaller scale. What do you say about that?
There's a famous dictum that goes back to Sidney Brenner. When we deal with complex systems, biological ones, which have structure on many levels, that in order to address such problems, you work from the middle out, as opposed to something you might be led to believe you should start with, which might be the genome. Were you to believe that, you know, the genome had a blueprint for all of us from life to death, I think most of us recognize that's nowhere near the case, and genome and gene expression depends on things going on at higher levels and indeed outside ourselves. So the issue is typically what kind of disease case are you working on? Where do you start the representation? And if it's going to be for surgery and cardiovascular diseases, you're going to typically be working on the scale of things that are represented, let's say, by continuum mathematics, complicated partial differential equations, and so on. And what you need to do is inform those models with information that might come from lower scales. It could be that you're worried about the transport of ions and maybe drugs across cell membranes in the composition of the heart. So you need to be able to capture that information as something that you can couple in. And from a technical point of view, the challenge that I think you're also hinting at is that from a computational perspective, the timescales on which one can do these simulations and the timescales on which some of those processes occur are dramatically different. So there's a huge challenge in getting what you'd call load balancing into simulations that can carry all of that information along together. And sometimes you do need techniques that are being developed in AI, machine learning, like surrogate modeling, that reduce the complexity and the computational effort of some of those so that you can keep the whole show on the road to implement the actionable decisions you referred to, because we really need to get these simulations to make predictions ahead of time, not after the event, so they can inform those clinical decisions.
Yeah.
Yeah,
in fact,
I can imagine.
You kind of, just to jump in there, you know, a lot of medicine's done with post hoc rationalizations of what happened. And obviously what we're trying to do is to flip things around so you can predict things. And it's really horses for courses, depending on what question you're asking of your model. You know, clearly if you simulated the heart from the atomic level upwards, it's going to take millennia for each beat, you know. Right. So you've got to craft your model in a cunning way to give you useful answers. Yeah.
Yeah. Yeah. And especially, I think the video is mentioning that you might want to do something like help someone guide where a stent gets placed in surgery. So obviously you can't then wait 10 years to find out. Yeah. So one of the other challenges that you talk about in your book is the need for almost like a cultural revolution in science to get more theory-based biological science efforts. Can you tell us a bit about this and what the gap is here?
I'll come in with oh, sorry, Peter. Sorry, forgive us, audience. Peter's in Boston. I'm in London, so we're talking over each other a bit. Go on, Peter, you carry on.
This is an important point because, in terms of digital twins and the technology for those as it stands today, one of the most demanding and challenging is in climate prediction. But that's an area that typically is regarded as being in the physical sciences, and the physical sciences are famous for being able to develop theory that makes predictions that then controls the way in which people conduct experiments. You only have to think of things like Einstein's prediction of gravitational waves, which took 100 years to be demonstrated to be true, or the discovery of the Higgs boson 50 years after the prediction to a discovery experimentally, let alone Turing's theory of the chemical basis of morphogenesis that took of the order of 40 years to be confirmed in the lab, to indicate that those are highly influential ways of developing science. When it comes to predicting the weather, we expect the weather prediction to be done ahead of when that weather is forecast, and we take that prediction very seriously. In the biological and medical sciences today, it's still the case, as Roger was indicating, that there's a kind of expectation that theory and modeling and simulation only comes in to explain observations and after the event. Well, for as long as that's the case, you will never be able to make predictions of the sort we're talking about here. They need to be credible, high-fidelity simulations. So they also need to be endowed with reliability and what we would refer to as, uncertainty quantification that confers on the predictions knowledge of how reliable they're going to be. So you have to have all of that in the play. And the biologists and the medics themselves have to begin to understand the importance of being able to rely on these predictions rather than saying, no, I can only rely on something when it happens and explain it after the event.
Yeah. Yeah. And Roger, you had a point on this as well.
No, well, I mean, it's. I just really wanted to say at a very kind of human level. For example, we consulted quite a few heavyweight individuals for the book. People like Roger Penrose or Craig Venter, and we also talked to Paul Nurse, who runs the Crick Institute, and this is something that Paul is really animated about. That there's almost, and this is going to be a shocking revelation for people in Google. He thinks there's too much data in biology and not enough understanding. And we really need to invest a bit more effort into theory and understanding what all these data are trying to tell us.
Yeah. Yeah. And I think another thing that you guys talk about is maybe moving a shift away from the approach where you have this big data ML approach, where you're kind of doing these black box causal understandings about relationships, as opposed to taking something that can capture a bit more of the mechanics of the process. Is that something where that's also like a mind frame shift that you see needing to happen?
I think it's in the context of the life of medical sciences, it's part of the same thing we're referring to, because ultimately the champions of this methodology must come from medicine. They must be understanding the methods that we're talking about. Now, there is a lot of complexity, of course, in biology and in medicine. And so one of the challenges for theory and the simulations is being sure they can handle all that complexity reliably. There will now always be room for combining the data-intensive methods with these, if you like, physics-based modeling methodologies, because the complexity of the systems is so large that becomes necessary. So we're not saying we don't want the data-driven stuff. It's more of a happy combination of the two. Typically, we'd like to see machine learning methods being applied that actually understand the structural characteristics of the problems we're we're working on, and that does require some theoretical basis. Otherwise, they're in danger of making predictions that might actually violate basic laws of nature, and that would be dangerous. So it's just keeping them under control. But their role can be very powerful, and I hinted at that earlier, in accelerating some of the calculations that otherwise would take far too long on these machines, even if they're the most powerful ones we've got access to globally.
Yeah, Matt, we've coined a phrase in the book, big AI, which is a little bit toe curling, I must admit, for some people. But all we're trying to say is that, obviously we're fans of things like AlphaFold and the amazing work that DeepMind has done, on that problem. But we think in general, it's very powerful to kind of moderate AI with physics-based intuition. And so that's what we mean by big AI in effect.
Yeah, that makes complete sense. And you're mentioning that some of this work, AlphaFold specifically, comes from DeepMind. When you're looking at these larger sort of modeling of these complex systems, where is this science coming from? Is it like research labs that are doing this? Is this like governments that are working on this in like large scale efforts?
I think
kind of a
the answer to that is that it can only ultimately be very effective on a global scale. And just to let you into a secret, one of the reasons why I'm in the US at the moment is to discuss setting up what's called a virtual human global summit, the first of which, if it is to come off, might happen by the last quarter of this year. Will be held in the USA. But it's in recognition of the fact that these problems are hugely challenging, and different bits and pieces of them can be done are being done in different parts of the world. There are different methodologies being applied. We've just talked about physics-based and sort of machine learning, and it's a combination of modeling and data-driven approaches, and who's involved, including the likes of Google and your own competitors, Microsoft, and so on. And then there's a big element inside the US with the DOE. Particularly, you're probably familiar with some of the things they're doing with Biden's cancer moonshot and the moonshot 2.0. It's all about trying to bring powerful supercomputers and data analytics methods together with, in this case, cancer problems, and trying to help to crack those together. So it really is an incredibly interdisciplinary activity, and it depends very heavily on our ability to marshal technology. And ultimately, as you can see, to get results in a hurry, which are actionable rather than after the event.
Yeah. Yeah. And I suppose there's also this element of trying to also bring in lots of people to this effort and do sort of the public evangelizing that you guys do with writing books and things like that. What's kind of the key message that you're hoping to get across to people who are maybe on the fringes of this effort or not necessarily know if they want to get involved in these types of scientific efforts?
Maybe I'll jump in first, Peter. I mean, Virtual used the first book about human digital twins aimed at a general audience. And actually, we worked really hard. I mean, one of the curses that we face is actually the Hollywood use of virtual actors and so on, because a lot of people think, well, Hollywood does that routinely. What's the big deal? Well, these are literally skin deep simulations. And obviously, we're talking about hearts that not only look like a human heart, but actually they behave like them, right the way down to the molecular level, following really the story of research that goes back to the 60s, a guy called Dennis Noble in Oxford, doing the very first heart cell mathematical models. And I think what we wanted to what we really wanted to get over in the book is that actually medicine is surprisingly backward looking in some respects, and that actually we're poised on a kind of new era for medicine where it can be truly predictive and truly personalized. And again, maybe just to mention one thing about genetics, I wrote a lot about the genome revolution, and I edited Craig Venter's books and so on. And in 2000, there was a lot of talk of personalized medicine. And then that got turned into what's called precision medicine, which actually is less precise than personalized medicine and based on anyway, the genome is really useful and really fundamental, but it's not quite delivered that vision. But actually, what we're outlining in the book is a way to deliver truly personalized and truly predictive medicine. So we drag people through a lot of big areas as well, whether it's AI, whether you can believe in what computers can tell you, and so on, just to make that point forcefully.
Yeah, definitely. Yeah, and I think you've obviously had lots of experience as an author and as a journalist in doing this task that you mentioned of like trying to take these complicated scientific topics and present them to a general audience. What were some of the challenges in doing that with this specific context of virtual U?
I think the biggest challenge, as I say, was just trying to help the audience understand, the current state of medicine and where it has to head. Also, ultimately, we're talking about sort of bringing mathematical models to life on a computer. There are no equations in the book, but we do have to talk about maths, and that tends to be quite a scary subject for people. And there are also some, I think, really big and interesting questions, like, can you simulate, is there an algorithm for every natural process? I'm not sure there is, actually, which is kind of fascinating in itself. Can you simulate everything on a digital computer? Well, Peter's done fascinating work showing that actually there are quite profound limits on what digital computers are able to do. We take people to a sort of future where medicine's personalized, where we might have to redefine what we mean by being normal. But on the way, we take them through a lot of interesting issues, including the limits of AI and, the limits of computers, you name it.
Yeah. Yeah. And you mentioned there that there's these theoretical limitations, and we can maybe get briefly a bit technical for the engineers in the audience, but there's the concept of, uncomputability, and that there's some things that we know can't be computed. How much does that play in here when we're looking at these sort of human level complex systems versus it's maybe more of a theoretical thing that doesn't actually show up?
So that goes to what Roger was saying, and you're asking us to develop a little bit. Right. The challenge here is around the fact that for most systems which are complicated, and they all are for real living systems, we may be able to construct a mathematical representation, but then we put it on a computer, and there's a step in what we call, the set of things like to check on the reliability of your methods, uncertainty quantification, validation, but another one is called verification. And verification is all about checking whether the mathematical model that you've written down is one you're actually implementing and solving in the computer. And that touches on or goes to the very heart of this problem. And the difficulty is that very often the only way you can check and verify that you've implemented it correctly is if you know the mathematical solution to the problem in hand. But for most real world systems, that's not accessible. So that's why we start with very simple systems that do look ridiculously sort of abstract and irrelevant. And one of them is called the generalized Bernoulli map. It just has one variable and one parameter. But the shocking truth of that is that, well, on the one hand, we have an exact analytical solution for what we call the invariant measure, or the probability distribution for how that system develops over time. And it's just an iteration of a point between noughts and one. It's utterly trivial. But it turns out that with floating point numbers, when you try to solve the problem with those, and you can compare it with the exact solution, there are some embarrassingly big differences for certain values of the parameters. And indeed, some of the false results don't depend on the precision of the simulation. So it doesn't matter whether you use single point, half precision, or double precision, you will miss huge aspects of the problem. So this is actually profoundly worrying, but it might be dismissed because somehow we're not comparing it with a real world system. On the contrary, it suggests that even if it occurs for such a simple system, we're going to be encountering it on digital computers. It's just that we don't know enough about it to be able to verify these mistakes, such as they are. So there's one way around that, and I think we alluded to that, and Roger was talking about it with analog computers. If you can implement the solution of some of these problems on analog computers, that's the closest you'll get to the exact behavior. And then you can compare that with the digital solution. And that's work that still needs to be done. to be able to, verify the implementations in many cases.
Yeah, that makes sense. Yeah, and thinking a bit more about kind of the sort of public relationship piece, obviously we just came through a big pandemic, COVID-19, that's kind of really, I think, changed how the public thinks about science and how they engage, especially with modeling. Yeah. How do you see that shift? Like, what do you think has happened in that shift? How are people now thinking about modeling and thinking about science?
It's a really complicated question because it kind of depends who your audience is. I mean, I think modeling in the pandemic was really an important use of digital twin, almost virtual populations, but obviously they were relatively crude models. And of course, I think if you talk to, shall we just say, people who are right at the political spectrum in the UK, what they love to say is something like, the model predicted 500,000 people would die. We locked down the whole country. And of course, it's not really only, 200,000 people died. Therefore, the models were rubbish. Well, of course, the models suggested that a lockdown was necessary. It was almost the only one of the few things that we could do, albeit the lockdown comes in many flavors and types, without a drug or a vaccine. And I suppose it comes to the old joke that all models are wrong, but some are useful. I would still argue that actually it is better to have a group of modelers with maybe an imperfect model at Imperial and London School of Hygiene and Tropical Medicine and elsewhere, trying to make sense of the pandemic, than a minister kind of sticking their finger in the air and saying, actually, I think we should do this or we should do that, and just guessing what to do. So it's slightly political how you accept the importance of modeling. Peter, I don't know whether you want to jump in on this before I embarrass myself and get into trouble.
I mean, the most interesting thing in a way was that suddenly in front of the whole general public, this was definitely the case in the UK, almost every day on major newspapers, they were reporting the predictions from some of those models. So this is precisely what we're talking about with computational biomedicine. We aspire to make predictions that are actionable. And nothing could be more important than predicting the number of, say, cumulative deaths. I got involved in some of that work as a function of time after you determine the pandemic has been initiated. And that was effectively happening with these models where Boris Johnson was determining to go into lockdown. What was missing there at the time was a proper understanding of the uncertainty that Roger's effectively alluded to that those models have. And we did a lot of work to unravel the uncertainty quantification of the pandemic models. And they do accommodate a very wide range of probabilistic outcomes. And indeed, it looks very similar to a weather forecast activity. And you have to be able to understand probabilities, which is often a challenge to the political class in terms of evaluating models and so on. What seems to have happened after this, unfortunately, is we've regressed to not worrying about predictions again. And I say that with some authority because a former PhD student of mine was working in that unit in the 10 Downing Street for a while, and it was all about predicting things for the pandemic. But as soon as it was determined we were effectively out of it, that unit got disbanded and no one was any longer interested in trying to use these kind of predictive methods, which is a disappointment, I would say.
Yeah, because it definitely seemed like there was this public awareness and then this public engagement with it where people who, as you mentioned, hadn't previously been speaking about or talking about, probabilistic modeling and even just thinking about what goes into a model. And then suddenly people are talking about it. And then to have that vanish, I think is definitely quite surprising.
Right.
We have a couple of, oh, go ahead, Roger.
Oh, no, sorry, but it's great you raised it because it's a really potent example of where we think medicine should be heading. It wasn't perfect by any means, but it was useful, and actually we want to see more of that and in different spheres of medicine.
Yeah, definitely. Yes, we have a couple of audience questions I was going to jump to. We have a question from Alan who says that this is fascinating. If we're able to predict and match the electronic signals for heartbeats, for example, what are the plans to also predict altering brain chemistry / activity?
That's a really hard question, so I'm going to leave it to Peter, actually.
So, I mean, Roger was already alluding to that partially with the reference to the epilepsy clinical trials and so on. There's a lot of work that does go on to monitor the electrical activity in the brain. And it's such a complicated and multi-scale problem. It does depend on what level you're trying to extract that information and to deliver things that might be of clinical significance. We were talking about the connectome. In fact, here where I'm in Boston, I heard a colleague in Oxford talking about that, and I know Google's involved in their work, which is basically looking at fruit flies, flies, and wasps at this moment to try and understand the connectome. And they tend to just look at a static image of that at one moment in time now and try to infer some kind of structural characteristics for the connectome. But in reality, that's just a completely potentially unrepresentative instant in a brain that's undergoing massive dynamical change. So the dynamics of this thing and the scale at which you study it are challenges here. And that's, of course, the message of complexity is don't necessarily go into too much detail, because you do that at your peril. The emergent properties may look quite different. And I would say for the brain, you know, that area is going to take us another, 50 years or more to get on top of. But that doesn't mean we can't use partial information and modeling along the lines we're talking about here. After all, the electrical responses there are nothing other than those along axons and neurons firing. I know that's beloved in the AI and machine learning as a representation, but in the brain, it's the same processes we've got underpinned ultimately by the Hodgkin-Huxley model, which is now folded into the human heart models, which are multi-scale and incredibly effective. So we have that instance of how we can integrate that type of information in front of us. And we just need to keep going with the brain to achieve something similar at much greater, complexity and cost.
Yeah, and I think the question also kind of hints at this point, which is that obviously there's huge ethical questions and moral questions around some of the stuff that you could do if you understand these systems and can model these systems with precision. How important are things like openness and transparency when it comes to the models and the software that we're using in this effort?
I think that's undeniably a very important question. And I'm going to say something, and I'm sure Roger will as well. In ethics in these areas, like in AI and others, really is important. And trying to make sure people understand when they're developing the methods is vital. What's at stake and interesting in a positive sense there are things like what's already being shown from these in silico clinical trials we mentioned earlier, that, if we use human data in simulations, it's already becoming clear we can get more reliable predictions of the action, say, of drugs on and outcomes on the human heart in the population than we can by using what are called animal models, which are actually testing things on live animals, which is often regarded as abhorrent. And then there's the actual participation of humans in clinical trials, which confers risk on them. Whereas if we can take them out of the equation, then we're going to benefit from that. So there are a lot of things like that, which are very good news. There are people who think that this avatar of us will be conscious and might endure pain when we operate on it virtually and so on. And it's just so vital to have the conversations now about something that's coming so we all understand it. So that's my take on that. And Roger, please let us know your thoughts.
I think, Matt, the good news is quite a few of the fundamental ethical issues are already covered off by existing debates. So, for example, data confidentiality is a key thing. Predictions, do people want to know? We've already got examples, say, in classical genetics with an awful disease like Huntington's chorea. Some people just don't want to know whether they're going to develop the disease. And so, this is already paving the way for the use of digital twins in human medicine. But I do think there might be some new issues. So, for example, you might think you're normal and healthy, and your friends and your partner might think that you're healthy. But if we've reached the sophistication that we can run digital twins of you with a range of potential lifestyles, it could be that your digital twin is saying to you, in effect, look, Roger, you know, that 3 bottles of claret every night really isn't such a great idea. And in fact, you're technically unhealthy because you're heading for fatty liver disease or, you know, whatever. So I think there are going to be some interesting new issues. And of course, it will also, there's always been a debate about enhancement, you know, the use of gene editing and so on to make people superhuman. And clearly, digital human twin technology will make it easier to predict what sort of modifications could enhance someone to make them well beyond normal in capability and so on. But the good news is a lot of those debates are already out there. But I'm glad that we're talking about that now, as it were. And also, that's why one of the reasons why we wrote the book.
Yeah, definitely. Yeah, so we have another question from Ivan who asks, it seems humanity is at least many decades away from understanding all of the biochemical processes in human bodies. How does this impact the quality and fidelity of simulations that we can do today?
I mean, I can jump in with a quick, easy answer. There's already a lot of things we can do. I mean, you're right. If you said, let's have a fully functioning, total digital doppelganger of Matt, I think that's some decades off. But if you said, you know, would Matt respond better to this drug or that drug? Peter himself has already run simulations that can give you actionable advice on whether this drug would work better on you and that drug might give you side effects. But Peter, maybe you want to give a deeper, richer answer than that.
No. The point is that there are always going to be things that you can improve the models by adding in. And that will happen. I mean, if, in a sense, this is an agenda for, let's say, 21st century medicine, to try to set it up in a way that produces more insight and scientific understanding in a framework which allows you to add progressively more information with time going by. But it would be a fallacy to suppose that this is like a step function where until we have fidelity at, say, 100%, whatever that means, we can't run the models and they're of no benefit. It's much more like a sigmoidal curve in which the information we have already is benefiting, let's say, the clinicians in taking certain actions. But as we build more insight, we can make the models more complicated. But remember, once again, since these are models, they're never going to try to be ultra, complete faithful representations. It's not serving anyone's interest to make them more complicated than they necessarily need to be. And that's the issue here, is how much of the data that we can put into the models is useful in order to help with actionable decisions. It's very much the same as you get in climate prediction, where people need to carry a lot of information, let's say, about chemical processes in the atmosphere, which can become incredibly complicated. And there could end up being hundreds of thousands of processes that you could build into these models. And the issue is how much of that detail does actually affect, let us say, whether the climate or the heat, the temperature of the surface of the Earth is going to be 6 degrees higher by the end of this century. Such information often may not be that relevant to the problem in hand. So it's a matter of assessing that and using theory and sensitivity type analyses to work out the importance of these processes.
And in fact, one very last thought, Matt, the fact that we've got regulatory agencies like the FDA already accepting digital twin research, and that we've got commercial companies developing digital twin software, shows you that we are entering the era of virtual you.
Yeah, and that makes total sense. And as we start to wrap up here, I wanted to just ask about kind of forward-looking the future. Are there areas of research or technology that are kind of on the horizon that you guys think are exciting and will be big steps in this process? Or what are you thinking about that?
Peter, maybe you should talk about linking your circulation model up, which is quite exciting.
Yeah, I mean, as each individual, let's talk about the organ systems. You've got the heart, the blood flow, you've got the lungs and all kinds of things. At the moment, there are individual projects that are developing these things as components that are tried and tested and being shown usually to work with personalized parameterization, etc. And it's a bit like a big software project of any sort to go to the next level, you need to integrate these components. So you don't throw them away and build them from scratch. And you, as a whole, you start to link these things together with all kinds of software and glues. So the ability to do a closed simulation of the circulation with a heart model of the kind we were referring to earlier, which typically, it's taken 15 years or more to develop by Barcelona Supercomputing Center. Right now, I'm working on a project with them that couples that to our circulation system called HeMel-B. These are very large codes that run on big machines, and now we want to put them together. And you can see over time, we will get more and more into those representations, and they can then address new aspects of medicine that typically haven't been looked at before because they have a more holistic element edge to them. There are these new technologies we're always interested in, and Google's clearly very interested in them as well. And quantum computing has some promise there, as we all know. If we can get past the NISQ, or noisy intermediate scale quantum era we're stuck in at the moment, where we're dogged by noise and having to do a lot of error mitigation, perhaps we'll get to a point where some of the types of calculations we're interested in for, drug discovery, for instance, will suddenly become much quicker to get answers for. And anything that accelerates our ability to run these types of computations will be really welcome in this field.
Yeah, that makes sense. And it's definitely an exciting future. And I think the vision that you guys lay out and the research that you highlight in the book is fantastic. That's all the time that we have. Peter and Roger, I want to thank you guys both again so much for being here. This has been an absolute pleasure.
Thank you.
Roger and Peter's new book, Virtual You, is available now wherever books are sold, including through your local and independent bookseller. For everyone who joined us today, we look forward to seeing you at our next event. Take care.